Well, hello and welcome back. We've got a brand new topic tonight, and this is a heavy-duty one. So take your time, take lots of notes, expect a good 30 to 45 minutes on this one. This is called related rates. So all in all, to find a related rate, we are simply finding rates of change with two or more variables that are changing with respect to time. So I do need you to pause it, copy down these steps, read them to yourself, and then we're going to go through 4 examples tonight. Okay, but let me just stress, do not get overwhelmed. This is a tough topic for a lot of students. We will work our way through it, but just, take your time and play with that pause and rewind button. So for everyone, we're going to draw a picture, and again, you're copying these. We're going to determine the rate of change we're trying to find, assign variables. We're going to look for some constants, write an equation that relates the two variables with respect to time, differentiate or take its derivative, and solve for the rate of change by plugging in the known information. So example number 1. A rocket rising vertically is tracked by a radar station that is on the ground 5 miles from the launch pad. So let's slow down right there, and in our directions there, the first step was to draw a diagram or picture of the situation from the problem. So we have a rocket rising vertically. Hopefully you can picture that. Okay, so I'm just going to put an arrow that's rising vertically. It is tracked by a radar station that is on the ground 5 miles from the launch pad. So my rocket is coming out of the launch pad, of course, and I have a radar station 5 miles from it. So I think you can see that we are making a nice right triangle here. And I'm just going to go ahead and finish off the rest of that triangle. Now here's the question. How fast is the rocket rising? Well, the word fast is asking for a rate. How fast is the rocket rising when it is 4 miles high? I can put a 4 here. And its distance from the radar station is increasing at a rate of 2,000 miles per hour. So let me just slow down and figure out what we have and what we're trying to find. So I've got 5 miles from the launch pad. I'm going to stick miles on the end here. I have 4 miles high. And I currently don't know how many miles this side is. Would you agree with that? So that's the first thing I'm going to go figure out. Watch my units. This is in miles, this is in miles. I need this side in miles. So you're probably guessing what to do. You've got two sides of a triangle. Nice little geometry, the Pythagorean Theorem there. And I'm going to assign some variables. I'm going to call this A, B, and C. And I suggest you do the same thing. Assign some variables to the problem. So I'm going to say A squared plus B squared equals C squared. My A was 4 miles, so that's 16 plus 25 equals C squared. So I've got 41 equals C squared. Therefore, it's not going to be pretty. It's just the square root of 41. And I'm going to go ahead and label that the square root of 41 miles. Okay, now again, take notice of those units. Miles, miles, miles. Now, let's get into the meat of the question here. How fast is the rocket rising? Okay, so again, how fast is the rocket rising? I want to know something about this side, but I don't want to know how many miles. I want to know its rate. So to represent the rate of this side, if this side is A, its rate with respect to time is the derivative of A with respect to time. So we call that dA dt. And I'm going to put dA dt question mark. That's what I'm trying to find. Now they give me one other thing. Notice the units of this. It says 2,000 miles per hour. I want you to jot that down and write the word rate under that. When they say miles per something or anything, feet per second, they're giving you a rate. Now, which side is 2,000 miles per hour? Well, let's read it again. How fast is the rocket rising when it's 4 miles high and its distance, the rocket's distance from the radar station? Rocket's distance, radar station. This side is increasing at a rate of 2,000 miles per hour. Well, if this side we just described as C, its derivative with respect to time is dc dt. And because they said increasing, that represents a positive 2,000 miles per hour. All right, so let's kind of recap on what we have here. We have 3 known sides now. We know the rate of this side. And I'm finding the rate of this side, that means I must know something about this side. Well, if you look back in our directions, number 4 says assign constants only to things in the problem that are not changing. Are any of these sides guaranteed not to change? Well, if the rocket's rising, clearly this side is changing. And as the rocket goes up, would you agree this side is changing, depending upon how high the rocket is? But what's never changing in this problem is the launch pad and the rocket station are always going to be 5 miles from each other. Think about this. Your house and the school are always going to be the same distance from each other. It's not going to change. So what I want you to do is, in big letters, I want you to write the word constant here. And we love constants if we have them. All right, so at this point, if I've gone too fast for you, slow it down, rewind it, and try it again. Basically, I've labeled my picture. I found any missing sides that I could. So I knew 2 sides. I had to go get the other side. Little Pythagorean Theorem. And I identified who I'm finding, what I have, and I have a constant if I have one. Now, step 5, I believe, it says write an equation that relates the variables with respect to time. So basically, again, I have a triangle. I'm going back to my Pythagorean Theorem. A squared plus b squared equals c squared. Now, I want you to put this in your notebook in a big star. You can only substitute if, before the derivative, if you have a constant. And that is why we love constants. Okay, you can only substitute before the derivative if you have a constant. So was A, B, or C a constant at all? Well, remember, we said this distance is never going to change. So 5 is a constant, which is side B, and that means I can plug it in before I take the derivative. So I'm going to rewrite this as A squared plus 5 squared equals C squared. And if you want, it's probably easier, is A squared plus 25 equals C squared. Okay? So now my goal is to take this guy's derivative with respect to time. And it's simple. You're just going to bracket everything in, and you're going to slap a d dt out front, implying take the derivative with respect to time. So the other day we took the derivative with respect to x when we did implicit. We're doing the same idea. If this variable and this variable don't match, then we're going to slap a d whatever dt. So the derivative of a squared is 2a. A does not match t, so dA dt. Again, here's why we love constants. The derivative of a constant is 0, so that's gone. The derivative of c squared is 2c. Those variables don't match, dc dt. And now it's pretty nice. Now you just substitute everybody in. Since both sides have a 2, I can easily kill that 2. And I'm just going to look back at my information. In my picture, a is 4, dA dt is what I'm finding. C is radical 41, and dc dt is 2000. So we said A is 4, dA dt is what I don't know, it's my variable. C was radical 41, and dc dt was 2000. And lastly, I'll just divide both sides by 4 to get my dA dt. 4 goes into 25 times with 2 extra zeros, so that's 500 radical 41. Now, you're not complete until you get some units on this sucker. Well, think about this. You found the rate, so you know it's something per something. And if I look back, everybody was in miles with respect to time of hours. So I'm going to say this is miles per hour. And that, my friends, is our final answer. Now, nobody said these were easy problems. Again, I suggest at this time you pause it, almost replay it, and try to do it on your own again. We're going to practice 4 problems today. We've got 1 of 4 out of the way, but they're all very, very similar in style. So we're going to identify anybody, see if we have constants, write an equation, and derive it. Example 2. The height of a triangle is decreasing at a rate of 1 centimeter per minute, while the area is increasing at a rate of 2 centimeters squared per minute. Whew, don't even finish that question. Let's just try to get a picture of what we have. Now it says a triangle, but notice it doesn't say a right triangle. So I'm just going to draw any random triangle here. And it says the height of a triangle, so I'm going to put my height in, which of course is perpendicular to the base, is decreasing, let's highlight that word, at a rate of 1 centimeter per minute. All right, watch that four-letter word. That's got to become one of our favorite words this year, rate. It's going to be our favorite four-letter word. Rate represents your derivative. And who are they describing? Well, it says the height is decreasing at a rate. So they are giving us d h dt, the rate or derivative of height. Because they said it's decreasing, I'm going to slap a negative on there, and it's 1 centimeter per minute. While the area of the triangle is increasing at a rate of 2 centimeters squared per minute. Okay, so now they're talking area, so I'm going to use a capital A for area, and they say the word rate, so it's not area, it's the derivative of area with respect to time, or dAdt. And I'm probably going to use a capital A for area and volume and perimeter, or their corresponding variable. And it says it's increasing, so that's a positive 2 centimeters squared per minute. Now, if you miss the word rate, the unit should give it away. Again, if it's something per something, you better know it's a d whatever dt. Notice this 1 centimeter squared, so that squared should give it away that it's area. Area is square units, and something per something is a rate. All right, so here's the question. At what rate, so they want a derivative, is the base? So the question is, what is dB dt, the base of the triangle changing, when the height is 10, so I can put equals 10 for my height, and the area is 100. All right, so we know this section represents the base of the triangle. They want the rate of change of the base, specifically when the area is 100. So I'm going to slow down. I know I've got a lot of information going. And again, if I lost you at any of those, pause it and go back. It's important we get these notes correct tonight. And I'm going to say, they told me something about the derivative of area. So since I know the derivative of area, that's implying I probably need the area formula. So area equals 1/2 base times height. Okay, area equals 1/2 base times height. Now, since they brought up dA dt, the derivative of area, that's what I'm going to do. I'm going to take this guy's derivative, so bracket it in, with respect to time. Okay, now before I do that, I have to ask myself, is anybody going to remain constant? So the height can certainly increase, and the base can certainly increase and decrease. I would say I have no constants. Okay, it's not like you're a set miles apart from each other. This is going to get larger, this can get larger and smaller. So there's no constants, I can't plug anything in first. So I'm just going to carefully take its derivative. The derivative of A, of course these don't match, so that's dA dt, equals, read this out loud, this says 1/2 base times height. Okay, so just like our implicit, I'm going to go 1/2, bracket in my product rule. The first is base, the derivative of height is dH dt, plus the second is height, the derivative of base is dB dt. All right, at this point the calculus is done. We're just literally plugging in numbers. So they told me dA dt was 2 centimeters squared per second. Do I currently know the base? Well, I would say no. dH dt is -1. They gave us that up here, is -1 centimeters per second. So I'm going to leave a blank here. I don't know what that is, but I know this is -1. The height they told us is 10, and they told us we're finding dB dt. Okay, so now we have one little snafu. We should know everybody but dB dt. What piece of information haven't we used yet? Well, I would say we haven't used the fact that we know the area is 100. So I'm going to take my area of a triangle, so area equals 1/2 base times height, and I'm not taking any derivative, I'm just setting that formula equal to 100. So 100 equals 1/2 base, and remember the height is 10. So I've got 100 equals 5b, divide by 5. 5 goes into 10 twice, so my base is 20. So I have to use the fact that the base is 20 to solve this problem. So I'm going to say 2 equals 1/2. This is -20 plus 10 dB dt. Okay. Now you could take this 1/2 and distribute it. To me it makes more sense just to multiply both sides by 2 and get rid of it. So I'm going to get 4 equals negative 20 plus 10 dB dt. Add my 20, so 24 equals 10 dB dt. And I get 24 over 10, which of course reduces to, let's see, 2 goes in there, 12 over 5 equals dB dt. Now don't forget, you don't get credit until you slap some units on there. You found something about a base, and you found the derivative of base, so it needs to be a rate. So if I check back here, my units were centimeters per minute. So I've got 12 over 5 centimeters per minute. Now, since I got a positive answer, what is that telling me? Well, it's telling me that the base is increasing at a rate of 12 over 5 centimeters per minute. And the word increasing came because I got a positive derivative. All right, next example, another similar triangle one. A ladder 15 feet tall leans against a vertical wall of a house. So again, I would stop there and draw a picture. Okay, got a ladder leaning against a house. Now we're going to assume the houses are perpendicular to the ground, that they're standing upright. And it says our ladder is 15 feet. So can you picture a ladder leaning against a house? If the bottom of the ladder is pulled away horizontally from the house, so picture this is the bottom of the ladder and it's being pulled this way at a constant speed of 4 feet per second. Look at those units. Is that the side or is that the rate? Hopefully you're saying by now that that's the rate. So again, I'm going to slap some letters on here. I'm going to go A, B, and C. Therefore, based off that, that represents a rate because it's feet per second. I can say that is dB dt. Now, let's think about, do we want a positive 4 or a negative 4? If you picture sliding this ladder out, would you say this side is getting bigger or smaller? Well, since it's getting bigger, I'm going to say that that is a positive 4 feet per second. Okay, and again, those units give away my derivative versus the b value. How fast is the top of the ladder sliding down the wall? So can you picture this ladder coming down? So let's just put an arrow. This is coming down. So I'm finding d a dt. That's what they're asking for. How fast is that coming down the wall? Specifically when the bottom of the ladder is 9 feet from the wall. So bottom of the ladder, 9 feet from the wall. So they're telling me b equals 9. Okay, so let's slow down. We know this side is 15 feet. We know this is 9 feet. Could we easily figure out the feet of side A? Of course. So let's quickly grab our Pythagorean Theorem. A squared plus b squared equals c squared. We've got a squared plus 9 squared is 81 equals 15 squared is 225. A squared equals 144. Therefore, side A equals 12. So zero calculus involved. All I had to do is a little Pythagorean to get that side. And that, of course, is 12 feet. So now pay attention. You've got feet, feet, and feet. All those sides are good. All right, let's ask ourselves the famous question. Is anybody constant in this problem? And we love constants if we can find one. Let's think about it. This side, the ladder's going out. And as that goes out, this side's going to fall down. So those aren't constant, they're moving. How about this side? As the ladder slides down, is the ladder ever going to change size? Is it somehow going to turn into a 12-foot ladder? Of course not. So this side is a constant. So C, side C, is a constant, and that is going to come in very handy. Find those constants. All right, so let's set up our problem. Again, it's just a nice triangle problem. A squared plus b squared equals c squared. And remember, we started last time. You can only plug it in first if it's a constant. So I can say this is a squared plus b squared equals 15 squared or 225. I'm just going to bracket that in and take its derivative with respect to time. So we'll just run through. This becomes 2a, and then don't forget dA dt. Those variables don't match. Plus 2b its derivative is d b dt, equals the derivative of a constant is 0, and that's why we love constants. Now we'll just plug in everybody we know. So I'm going to have to scroll up here. I can kill those 2's. They both are divisible by 2. It's like dividing it out. Let's see, side A was 12, and I'm finding dA dt. Side B was 9, and dB dt was 4. So I get 12 dA dt. I'm going to subtract that over, equals negative 36. Lastly, divide both sides, and I get negative 3. Now again, let's slap some units on that. It is a rate, so it's something per something, and if we look back, we should see that it is feet per second. Okay, feet per second. Now, let's be smart. Why is that number negative? Think about what's happening. This ladder is sliding out, and this piece is coming down. So because this distance is getting smaller, we would say we have a negative answer there. But now, I might write it differently. I might say when I write it up, the ladder is sliding, and I want you to write the same out here, down the wall at a rate, there's my 4-letter word, of 3 feet per second. Now you might be saying, hold up, crazy lady, how come you didn't throw a negative on there? Well, think about this. I'm already telling you that it's sliding down. Okay, so this should imply to you that you're going to get a negative value. So I don't want to say negative twice. I'm sliding down at a rate of 3 feet per second. This is implying that you have a negative value. All right, we've made it to the last question for the night. A northbound ship leaves the harbor at 12 noon. So I'm going to start here and call this my harbor. I'm just going to make a dot for it. And it says it's northbound, so I know it's going north. And it leaves, I just want to make it's leaving at 12 noon with a speed of 7.5 miles per hour. So are they giving me the side or the rate of the side? Hopefully those units give it away and the word speed. So I'm going to say 7.5 miles per hour, that is a rate. And a westward ship, so now I've got a ship going this way, leaves the same point, the same harbor, at, I'm just going to make a note, 2 p.m. with a speed of 8 miles per hour. So again, they're telling me speed, my units are miles per hour, make sure you recognize that as a rate. How fast, so I'm asking for the rate, are the two ships separating at 4 p.m.? So I want to know the rate of change of this side, the derivative of this side, at 4 p.m. So I'm going to slow down and slap some variables. I'm going to call this A, B, and C. And I'm just going to make a note that dA dt, that's the rate of this side, is 7.5 miles per hour. dB dt, the rate of this side, is 2 miles per hour. And the question is, how fast is this side changing? How fast are the ships separating at 4? So I am looking for dC dt. I'm just going to put that with a question mark. Now, does this one feel kind of odd to you? Do you actually know the length of any side? Hopefully you're saying no. All I know is how fast this guy's going and how fast this guy's going, and I'm looking to see how fast this guy's going, but I don't know actually the length of the miles of any side. Well, use some common sense, and this pops up a lot. If you drive 7.5 miles per hour, how far have you gone in 1 hour? Well, 7.5 miles. How far have you gone in 2 hours? 3 hours. So here's the catch. We want to know how far they are at 4 p.m. So at 4 p.m., how many miles did this guy go north? Well, he started at 12 noon, so at 4 p.m., that would be for 4 hours. Would you agree with that? 4 hours? Now he can drive 7.5, or drive the boat 7.5 miles per hour. So I need to do 7.5 times 4 to get me 30 miles. Okay, so let me say that again. From 12 noon to 4 p.m., that was 4 hours, times 7.5 miles per hour, gets me a total of 30 miles. We're going to do something on the other side. We're going to say the same thing. However, this guy left at 2 p.m. So from 2 to 4 hours, to 4 p.m., how many hours was that? Well, I would say that's 2 hours. And remember, you can go 8 miles per hour, so I would say this is a 16 miles. Now, my picture feels a little sloppy for myself, so I'm going to slow down and kind of re-sketch it out for myself. We called this A, B, and C. I said my side A is now 30 miles, and my dA dt was 7.5 miles per hour. My B, we came up with 16 for B, and dB dt was equal to 2 miles per hour. And the question is, we were looking for dC dt, and now we can easily figure out what side C is. We know A is 30, we know B is 16, so we'll just calculate a little Pythagorean Theorem off to the side. 30 squared plus 16 squared equals C squared. I'm going to grab my calculator, which I probably don't need it for that, but I've got 900 plus 16 squared, of course, is 256, equals C squared. Therefore, C equals, if I add those together, I think that's 1156, and it's the square root of that. Now, that doesn't look like a perfect square to me, so I'm just going to say C equals the square root of 1156. All right, now the famous question. Do we have a constant? That is what I'm looking for every time before I start my calculus. Do I have a constant? Well, this ship is traveling up. This ship is traveling this way, and as they separate, the distance is changing. So I would say no, I don't have a constant. So I cannot plug any terms in before I derive this function. So I'm just going to start off with a squared plus b squared equals c squared. Take its derivative, 2a dA dt plus 2b dB dt equals 2c dC dt. Everybody, of course, is divisible by 2, so I can kill those 2's. And let's just carefully substitute in. We said side A was 30, and its rate is 7.5. Side B was 16 at a rate of 8 miles per hour. Side C is the square root of 1156, and we are looking for dC dt. So here's where I'm going to steal my calculator. I'm going to obviously put this side together. And I get, let's see, 353 equals the square root of 1156 dC dt. Divide by my square root of 1156. Now, of course, if it was in the non-calculator section, I'm leaving it like that. If I'm allowed to use my calculator, I'm just typing it in. So I get dC dt is changing at a rate of, I'm going to say 10.382. And because we were talking about miles per hour and this is a rate, I'm going to slap those units on there. Well, again, this is a big topic for us, so please take your time. Do not get overwhelmed. We will practice for an entire week, and we'll just change the shapes slightly. So take your time tonight, and we'll see you tomorrow.